All right, so we're going to kick it off. Thanks a lot for coming in person and also remotes. We have the day 3, the last day. So the way we're thinking about this session is to basically have it divided into 2 parts. The first part is be focused on the theoretical part, and the second part we're going to focus on the hands-on lab. And also, I discussed with Amir that we're going to stay till 10. I'll be around if you want to stay around and just play with the labs. I'll be around to basically work on the labs and obviously go through any problems on the capstone or also on the labs you have. And also definitely we have some, I assume, TA hours left. And also just after this session, if you have any problems or anything, just ping me. We're going to take it offline and connect it basically to go through any problem you have. Beautiful. So before I start, any particular question that you have from the concepts from the last session? If there's anything from the bug or any kind of errors you're getting on the code, please leave it aside for the last part. But if you have any question about the concepts or the theoretical parts, please let me know. We're going to go through that first. Yes, please.
So it is a bit more practical that you might want. So in the notebook that we ran at the last session, at some point I realized that the workspace or the experiment object is aware of a GitHub repository. I'm not quite sure how did it find out about it.
So do you remember from the first session you had to .git within your directory? Okay. So whenever you have git in it, you actually create a .git as a hidden file in the current directory, right? So whenever you start an experiment, and if the experiment finds that you have a .git there, it actually, do you remember also there is a head within the git concept, which refers to the latest point in the current branch and also the latest commit. So the head refers to that. So it actually fetches the information for the head of the current branch. So if you are in any branch or basically you're in any kind of particular git commit, it will basically connect it to the experiment, so you will basically able to track it later on.
And another little thing, could you clarify at what point did I authenticate on Azure from my Jupyter notebook?
Yeah. So do you remember the first tops, I think the third or the second cells, you provide in your subscription information, yes. And the second cell, you say, hey, I want to connect to Azure Workspace. So if you are already logged in, you don't have to do anything. But if you're not logged in, it will prompt you to basically log in yourself, and it will go back to the browser again. Yeah. That's the place. And also today we're going to focus on different type of also authentication, because that's an interactive way where you're sitting behind us. But if you're running that application through an agent or an application is running that instead of you running that code, you need a different type of authentication, which we're going to focus today.
And another small point.
Yeah, sure.
So in the run object, there is a property or something with child runs. So are they run objects nested, or are they in a sequence?
Yeah, so by default, it is not nested. So you have one parent run, which is the only thing you have. But if you have tried the hyperparameter tuning or hyperdrive, or also AutoML, which is another different type of run. So within the hyperdrive, you basically have so many sub-runs happening under a parent run. So those are considered the child runs of the parent run. So each of those runs will get different parameters and also will produce different kind of metrics. Yeah.
Okay. And I probably am able to design it myself to run some sort of binary search or anything I please in that.
Yeah, exactly. When you say binary search, what do you mean by that?
Oh, I mean, I'm looking for a hyperparameter.
Yeah. So there are 3 types of hyperparameter search we can find. One is greedy, where you basically find one after the other and one after the other. The other one is random. Basically, you provide a random pool of samples. And from that samples, basically from that distribution and population, the samples randomly. And the third is by Bayesian optimization, which is a kind of a learning method, which from the initial experiments, it finds out what is the best guess, basically, is for the picking up the next option. Yeah. Awesome. Any other? You always ask good questions at the beginning. Any other question? Anyone on the line? If you could check. No one? Beautiful. So again, our amazing TAs. I apologize for Jake. I mistaken his. There was a typo with his name. It was not Jack, it's Jake, basically. And also, I add also Werner's last name again. That was missed from the last slide. They're amazing. Without them, it would be impossible to basically run this workshop. Thanks a lot for your support. And also disclaimer, like this workshop is basically doesn't represent any organization that I'm affiliated with. So it's basically all of my personal experience and my personal opinions, not reflecting anyone else's opinions. So today, yes, please. Yeah.
One online question.
Absolutely, yeah.
Can you catch my voice? Oh, okay. So the question is, how to let Azure know about the GitHub repo for the model not using web console? As in, how to register it programmatically.
When you say, could you elaborate on that?
No.
Could you repeat?
Okay.
Could you repeat it again?
How to let Azure know about the GitHub repo for the model not using the web console?
Yeah. So the model is not associated with a Git repo. The model is different from the Git repo. The code which generates the model can be associated to Git repo. If it is actually version, so wherever you're running your code and experiment, if there is a .git file and there's a git init happen within that directory, the experiment will catch it by default. So you don't have to basically introduce that. But again, the model is not associated with a Git because two different things, but the code which generated the model can be associated with the Git. Yeah. Awesome. No problem. So today we're going to focus first on how we can integrate our ML pipeline that we built in the last session into the build pipeline. Then we're going to discuss about deployment of the model. There are so many concepts we're going to go through, like Dockers, Kubernetes, the best practice around them, some of the different concepts about different consideration you need to think about when you want to think about deployments. Then we actually develop and create the release pipeline for basically to be able to deploy the model. And finally, we're going to discuss about some of the best practices around model deployment, logging, retraining, etc. Then after going through the theoretical concepts I mentioned, we're going to go through the labs for the second part of the day. Again, we're going to stay till 10. Please stay if you want to go through the labs together. More than happy to do it. Awesome. So the ML pipelines. Again, like recap on the ML pipelines from the last week. Each ML pipeline is basically a set of steps. Each step is completely independent, is Dockerized, and it completely works independently on using independent configuration on independent hardware. One of these steps can be executed on GPU, the other one CPU, the other one Spark cluster. It can be so many different configurations for each step, and each step can get a different data and pass another data. You can run steps in parallel or in sequence. So basically, that's the concept of the pipeline. But why we have a unique machine learning pipeline versus the other pipeline engines? The generic pipeline engines helps you to orchestrate generic jobs, any kind of job which is not machine learning related. But for machine learning related, we have a couple of unique concepts like metrics, like models, like deployment environment, etc., where it's unique for machine learning tasks, where this is different from any other types of generic tasks. Because of that, we build treat machine learning pipelines differently from generic pipelines. From the taxonomy of the ML workspace, which you have worked in the past 3 weeks, it is actually located here, which is separate from the experiments. But whenever you create a pipeline, when you execute the pipeline, it needs to be associated to an experiment. So if you see, whenever you run a pipeline, it has to be associated to an experiment, and it will be executed. So we actually had an example from last week that we're going to elaborate and we will build on top. So what it does, it is a 3-stage basically pipeline. If you remember the MNIST problem we tried to solve in the first week and the second week, we're going to actually make it much more complicated. Again, This is a simple example to show you the concept, but for your capstone, pick a much more complex one, but do not go very crazy, but just a little bit more complicated and a little more interesting. But for this one, although it is a simple task, I divide it into 3 different steps. The first step is data pre-processing. The second step is to get that pre-processed data and train the model. And the last step is to basically to register the model. The pre-processing, it downloads the files, normalize the files, like divides it by 255 to basically gets it the values between 0 and 1, and then saves it as a NumPy object in the processed in a data storage. And within that shared data storage, the training step picks up that processed files, trains the model based on those processed files, and then once the processed files are processed, it will basically save the model into output folder of the experiment. If you remember again, the experiment had an output folder, it will be saved there. And then the last step, it will pick the model from that output folder, and then it will register it into the model registry. So now this is like a 3 simple step pipeline, which is very similar to any complicated. If you replace that MNIST to any other problem, basically it just consists of these 3 steps: pre-processing, model training, and model registering, basically. And you can have like different kind of environments, because to speed up the process, we actually only use 1 CPU for all of them, like 1 CPU instance, but you can have like different types of compute engine for each of the 3 steps separately. Awesome. And then once you generate the pipeline, if you remember, you had to run this line where it basically publishes the pipeline. And once you publish the pipeline, it actually gives you an endpoint. An endpoint is basically a web API location, is a link where you can introduce it to anyone. So the good point is, like in your work actually, so once you build your machine learning pipeline, you can pass that link to your data engineers and ask them, if you want to basically train my machine learning model, you can basically hit this link and send your request to basically this API, and it will kick off. And then you will see like how once it is registered, you will basically be able to see these endpoints within the portal or the Azure ml.azure.com. Like these are 2 different interfaces. You can see that. The concept is very similar in Qflow. Again, the whole exact same concept. You'll build the pipeline, you register it as a link, and then you can host it as an API. No difference. Again, like the concept is very similar to like different ML operationalization engines, but like different syntax and different environment. Like the whole concept is exactly the same. Not really very different. So again, back to that use case, this is a very typical data pipeline, right? So this is a data factory pipeline, which is a generic orchestration engine. Like it builds basically sequences of jobs to run on Azure. These are generic tasks, like loading the data, running some ETL jobs on the data is completely data engineering and nothing to do with machine learning. But let's say once the data is landed to your blob storage, which is similar to your S3 or Google Cloud storage if you're not familiar with this. Once you load it here, if you want to basically let your data engineer to use and consume your pipeline is basically available. So you have published a pipeline, gives you the link, so you pass them, and then you basically can hit your pipeline whenever they want, right? So that becomes a consumable, separate pipeline, can be used from anywhere else within a generic pipeline or within an application or anywhere they want, or even external, because of open link, you can basically pass it to anyone. And then that pipeline will generate a model, and that model can be hosted to a deployment engine such as Kubernetes. And that Kubernetes can basically start to infer and save the data into like a data store like SQL or like Postgres or any type of database you have. So that chain will get connected from anywhere else if you wish. But the focus of this workshop is basically to orchestrate from CI/CD perspective. But again, this is another way to consume that pipelines that you generated, if that makes sense. Awesome. So some best practices around the building machine learning pipeline. So first, make sure that you use some random numbers or some random names for the disposable resources, because these disposable resources are used to be created and be deleted. And if you're running like multiple pipelines at the same time, and you're willing to invest more money to basically create dedicated resources per pipeline, then there will be no conflict between these resources if you have used some random numbers. But if you have used basically static numbers, they will get queued, so you won't be able to run like multiple jobs at the same time. Let's say if you're training to like, if the logic is the same, but you need to train like 10,000 models for 10,000 stores forecast, for instance, right? That 10,000 will get queued if you want to use only a single resource. But if you have used multiple resources, you can basically run them on 10,000 resources and then delete them after they're done. It's definitely faster, but at the end of the day, you will pay the exact same thing, right? You have to wait either 10 hours or like 10 minutes multiplied by basically 100, if the math is correct. I didn't calculate that. But then delete the resource after you're done, because that's the most expensive part of using the cloud, mostly. The resources which you use for computation are very expensive, but the rest are cheap. Use low priority VMs like spot instances like in AWS, and we call it low priority in Azure. Basically reduces the cost to like 1/10, but the problem is that they will get deallocated when someone wants to use them. But it's really good if you run it on like 100 nodes at the same time. The cost will be 10% of the actual cost, even lower. If you don't have like an SLA for the training to be done in a particular hour, if you're like can be more flexible, definitely can use that. You can use ML pipeline parameters. I didn't use it for this example, but within that link, which you can basically kick off the pipeline, you can pass in also some parameters, such as like within a query string. You can say like, use this data for me for this time, or even change the other information which you have hard-coded within the code, so you don't have to hard-code anymore. You can completely parameterize everything. And finally, make sure you don't keep your credentials within the code. Always use some sort of best practices within each cloud has its own. But like in Azure, key vaults or variable groups, where we discuss variables today, but there's also another way to save more secure way of keeping like credential like key vaults, which is more secure. But again, do not like hard code, especially if you have hard coded, make your repo private. Definitely don't public it, because everyone can use them. That's crazy. And yeah, so after publishing, you will basically be able to be triggered from any other resource, as we discussed. Going back to the first session, the Git, and the basics of the Git and branching strategy is different in machine learning than the software engineering. In software engineering, any new ticket has to be basically built and needs to be merged into the master, finally, one day, once it gets mature. But in machine learning, it doesn't work that way. Sometimes you do not even want to bring back an experiment to the master. So sometimes you want, but sometimes you don't want. So there can be some branches where basically you start a trial of an experiment and then you never merge it back. So, but the general concept applies. You have one master, you have one intermediate branch at least to be secure. Do not work directly from the master, and then you branch off for every new trial in our case. So if you want to start, like you have develop your model using a very simple method, you want to for instance, use hyperparameter tuning, you will branch out, add that, and once you're happy, you merge it back to the pipeline instead of working directly in the master. But again, it can be the case that some of the branches never get merged back to the pipeline. And also, if it is completely irrelevant to the pipeline or anything which is going to go to production, make it separated completely from that repo and use another repo to basically keep that code. Make it separated from the rest of the project, if that makes sense. So we have a couple of steps. So in the examples that we went through last week, it was a Python script which it executed the extraction, and also might have registered, and also use an estimator, which was a TensorFlow estimator in the middle. But also there are like 3 other types of steps that we can use. The first step is data transfer. Sometimes you just want to move data from one storage to the other storage, and you don't want to write custom code. You can basically use this, provide the first data storage and the destination. It will basically, the code is already developed. You can of course develop it yourself, but it makes it simpler. And also the last 2 are hyperdrive steps. We discussed about hyperparameter tuning and hyperdrive in the experiment reproducibility. If you remember, there was like a very simple, like 3-4 step, but it can be much more complicated and much more much more beefy somehow, like hundreds or thousands of iterations can be set. And finally, you can also use AutoML step. That's also another native AutoML, which is built within Azure ML, which you can also use at another step. These 2 last steps are very useful if you want to do retraining later on. Like the first steps basically is assuming that you have very static hyperparameters. You pass a set of hyperparameters, it gets trained. But assuming if you want to do retraining, the main reason of doing retraining is basically to get it always improved and always try out better parameters. And you want to automate that process because, again, going back to that 10,000 models you want to build for 10,000 stores, is impossible to have a human to fine-tune every of those 10,000s, right? So probably come up with the general concepts and then use a hyperparameter tuning, or completely go AutoML and start let them find the best model and also find the best hyperparameter for itself.
For AutoML, do you just like simply point into a data set?
Yeah.
Okay.
So you still provide a data set as an input, but you only say, I want classification or regression or forecast. That's it. Yeah. Problem category, and then it will come up with a combination of pre-processing, modeling, and hyperparameter tuning. Yeah. Yes, please.
For the estimator step, is the reason why like you'd want to have that instead of combining it with the Python script steps is because it's usually the frameworks are optimized for the particular cloud infrastructure? Or?
I'm going to get to that,
Yeah.
but to answer briefly, so it helps you to basically makes the preparation of the machine faster. So for instance, if you're going to use TensorFlow for GPU, you need to install like CUDAs, like CU, DNN, and some other packages, and also like you have to deploy a particular type of drivers on the machine. So that is pre-packaged, and the entire Docker will be shipped instead of like installing all of these packages basically for that version. Makes it much faster to deploy and make the machine available. But you can provide the exact same configuration to the Python scripts. I want all of these packages to be installed. I want you to basically ship this particular Docker image. You can write that, but it makes it abstracted basically. Yes, please.
Can you specify the version of TensorFlow or PyTorch you're
Yeah.
using? Okay.
We can specify the pre-packaged Dockers are supporting TensorFlow 1. So TensorFlow 2 is still not pre-packaged, the Docker, but you can use Python script and say, I want to install TensorFlow 2, or even you package your Dockerize your own, like you build your own image and then basically host it in Docker Hub and then pass that to the hyperparameter, to the step. And absolutely every different version of framework requires different types of dependencies and everything else. And there are 2 different concepts here. One is the data dependency. Again, if you remember, you could set different steps and dependency of the steps by defining the data dependency. You could say, I want this data to be the output and the same data to be the input of the next step. So that would build a sequence of the steps instead of you explicitly mentioning that these 2 happen at one after the other. And also finally, the pipeline endpoint, which is where you basically, once you publish the endpoint, going back to that code snippet that I showed, it gets published. So before publishing that explicitly mentioning, I want this to be published, it won't go under the pipelines. It will build a conceptual pipeline and you run it, but it won't be published, it won't provide you the endpoint. And the good point of the endpoint is every time you train it, it will get versioned. So you can also version the endpoints. So let's say like in the future, you want to go back to a particular version, you can retrieve that particular version you trained. if you don't mention, it always gives you the latest version, basically. Yes,
So
please.
like the data dependency part, like you've between each of the steps, right? Like you could have a broken pipeline just because like the schema of the data could shift, right? So like how are you like how can you ensure that the data that's being passed on between each step is consistent?
So the data is not physically passed. If you want to like correctly like yeah, the terms it will be the reference will be passed, like point out to this data point basically as the next step. But in terms of the data schema, why it should change between the steps.
So like for example, if the feed like say for you have maybe like a pipeline of like where you have a change in the feature set or something like that. You want to expand the feature set of a particular model, and maybe that, or like a particular part of your algorithm requires a certain number of feature set, and that's shifting. Then the input is going to shift as well, right? So how would you like? How can you
so
guarantee
that's,
from?
So that's part of the data test and the integrity test you have to basically apply. It doesn't do it automatically for you. But you have to basically make sure that that is not breaking your code. So most of like in the types of algorithm or methods that you basically may have changes in the data, like for instance an NLP problem, your like dictionary changes, you may want to basically have different set. So you mostly do not pass it in a schema way. You will mostly pass it as sparse matrix into the step. So that really doesn't break the code. But if you're really changing, like if you're basically working on a CRM project, for instance, and the actual field in database changes, it will change universally. So your entire pipeline will fail, for sure, yeah, unless you go and fix that within the code. Yeah. Also some like mechanism, as we discussed last week, that can basically save your schema somewhere as a shared environment. Basically, whenever you change your schema, everyone reads that from that shared environment.